This is a heating curve looking at ice beginning at minus 25 degrees Celsius and ending at plus 125. So what we're asked to do is correlate these different sections, 1, 2, and 3, with the correct states of water. So in this section here, section 1, what is the state of water? I heard ice, solid. Here we have a mixture of a solid and a liquid. At this point, we would have solid, this point and below. At this point and above, we're going to have a liquid. In between, we've got a mixture of the solid and the liquid together. So ice cubes floating in water. The temperature is going to be 0 degrees Celsius. How about section 2? What state is water in this section? It's a liquid. It's a liquid. The temperature is increasing, but it remains a liquid. And how about section 3? We've got liquid boiling, and so what we have are gas and liquid coexisting together. Okay? Any questions? When we do a calculation that involves changes of state and changes of temperature, what we have to do is either actually or in our mind draw a graph like this that's going to describe what's happening, and then for each line segment we will calculate the amount of energy and then we'll add them together. Okay, your book does not do a great job of explaining that. Let's do an example here that I made up, because your book doesn't give you one. Calculate the amount of heat in kilojoules needed to convert 1.00 moles of ice at minus 25 degrees Celsius to water at 37 degrees Celsius. So we've got two things happening here. We have, well, actually there's three things. We have ice warming up to the melting point. We have ice melting into a liquid, and then we have liquid warming up. So let's draw a picture of that. So if this is energy being added and this is temperature going up this way. We're starting with ice at minus 25. And so it's going to warm up to 0. And then it's going to melt, and then it's going to warm up to 37. That's what the question is telling us. We're starting with ice at minus 25 degrees Celsius, and we're heating it up until it's water at 37. Water is the liquid form. So we have a state change in there, and we have temperature change. So there's actually 3 different calculations that we need to do. For each line segment, warming up of the solid, melting the solid, and then warming the liquid. Let's do them in order just for fun. When you have temperature changing like you do here, your equation is going to be Q equals mc delta T. You have to use the appropriate heat capacity. See, I've got some formatting issues. Water there is supposed to be a subscript. The heat capacity of ice is different than the heat capacity of water. So going from minus 25 to 0, this is ice warming up, so we need the ice heat capacity. That's C. What's M? M is the mass in grams of the ice. Did they give us the mass in grams? No, they gave us 1 mole. Well, 1.00 moles. The molar mass of ice is 18.02 grams per mole. And so we have 18.02 grams of ice. So the mass is 18.02 grams. C is the specific heat capacity of the ice, 2.09 joules per gram degrees Celsius. And then the temperature change is the final minus the initial. So we're going from here at minus 25 up to 0. 0 is the final temperature. Final temperature is 0 minus the initial negative 25. Anybody have any questions? We did these kinds of calculations in an earlier chapter. 18.02 times 2.09 times 25. So this is 941. That would have technically 2 sig figs. I'm going to carry a couple extras. And the unit is joule. The degrees Celsius cancel out, the grams cancel out. Any questions? So we heat the ice up until it gets to the melting point. Then we figure out how much energy does it take to melt 1 mole of ice at the melting point, melting temperature. That's where we use the heat of fusion. This says that it takes 6.02 kilojoules per mole to make ice into liquid water. So 1 mole of water times 6.02 kilojoules per mole. That's 6.02 kilojoules of energy to melt the ice. So that's this part right here, melting the ice. Now we've got water at 0 degrees Celsius, but we're trying to get it up to body temperature, 37 degrees Celsius. So we're taking liquid water from 0 to 37. How much energy does it take to heat the water? That's Q equals MC delta T again. Q equals MC delta T. Well, the mass of the water is the same as it was before, 18.02 grams. But now we're going to use the specific heat capacity of water, which is different than that of ice. 4.184 joules per gram degrees Celsius. And then delta T, final minus initial. The final temperature is up here, 37 degrees Celsius, minus the initial temperature, which was 0. So I've got 18.02 times 4.184 times 37. And this is 2789.6. Again, only 2 significant figures. Joules. So what I need to do now is add these 3 numbers together to get the amount of energy for the whole process. Can I add joules and kilojoules? No. So I need to convert. These are big numbers, and I can see that my last significant digit is over here, and so I'm thinking that kilojoules is probably a better unit. Oh, and look up here. It wants the answer in kilojoules. So I'm going to convert joules to kilojoules, and then I'm going to add them together. So joules on the bottom, 10 to the 3rd joules is 1 kilojoule. So that's going to be 2.7896 kilojoules. And this one, Sounds like somebody's vacuuming in the hallway. Isn't that what that sounds like? There's no carpet. I don't know what they're doing. Maybe they're buffing the floor, because that's an awesome thing to do while classes are in session. It's not disruptive at all. The floor mats, I guess they have to do that sometime, but they would pick during my lecture, right? I'm running out of room. I'm going to put it up here. So that's going to be 0.9415 kilojoules. So I've got this number, and I've got that number, and I've got this number, and I need to add them together. .02, 0.9415, 2.7896. Yeah, syntax error. It's fine. What did I do? I pressed the wrong button. That's what I did. 9.7511. Anybody else get that? Thank you. Now, significant figures, we were adding. So 6.02, the uncertain digit is going to be the last one. That's the second decimal place, and this is the second decimal place, and this is the first decimal place. So I'm going to round this off to the first decimal place, and we're going to end up with 9.8 kilojoules of energy needed to take a 1 mole ice cube from -25 and heat it up to 37. Why you would want to know that, that's another question, but there it is, just in case you were wondering. Any questions? There could be a question like this on the exam.
This exact one.
There could be, it's possible, there could be this exact one, probably not. But anytime you have a state change and a temperature change, you have at least 2 calculations. There's no shortcut for combining these. You just look at each transition separately and you add them together. Well, could you equate the number of state changes to how many equations you have? Sort of, but it's temperature changes and state changes. So in my diagram here, I have 3 line segments, right? So that means I have 3 equations, 3 calculations, 3 numbers to add together. So I would really encourage you, even if you just make an ugly little sketch like this one, just to get a picture of what's going on. Each straight line is going to be a separate calculation, and then add them together. Let's talk about sublimation. Melting and freezing we're very familiar with. Sublimation is a little different. Sublimation is going directly from the solid state to the gas state without melting in between. Most substances don't do this. But things like dry ice do it all the time. So what happens when a substance sublimes is that molecules on the surface of the solid have enough energy to escape into the gas state and become a gas. And so they don't actually melt, they just escape into the gas state. The reason that dry ice is called dry ice is because it doesn't melt. Regular water, regular ice, you might call wet ice, because when you fill your picnic cooler with ice and you put the sandwiches in there, the ice melts and your sandwiches get all soggy because they're floating in water, right? And the Ziploc bag that's supposed to be waterproof never is, and you've got water on your bread and it's nasty, right? That's why people like dry ice. It doesn't melt. It doesn't make a mess. Dry ice will not melt at any temperature at atmospheric pressure. It takes a very high pressure to make it melt. It will actually begin subliming at minus 78 degrees Celsius. So it's very cold. Here's a photograph of dry ice. Dry ice is just solid carbon dioxide. They pull it out of the air, cool it down, and make it into a solid and sell it to you, right? It's just solid air, basically. But it doesn't melt. It goes directly into the gas state. Now, what we're seeing down here, it looks like there's like vapors or something that are falling down, right? What we're seeing is the cold gas that's escaping from the solid coming down, and because it's cold, it's causing water in the atmosphere to condense. So it's making its own fog, basically. But you can't actually see carbon dioxide gas. You're seeing the coldness causing water in the air to condense. Regular ice also sublimes, but it does so much more slowly than carbon dioxide does. But it will sublime at temperatures below its freezing point. I grew up in Minnesota and Iowa, where it gets truly cold. I know we feel cold outside today because it's only like 50 degrees, but in the Midwest it gets really cold. And it'll sometimes stay below freezing for a couple of weeks. Below 32. Sometimes even below zero for over a week at a time, Fahrenheit. But the snow and the ice that's out there will gradually disappear, even though it's too cold to melt. And it does so by subliming. Have you ever noticed that ice cubes that maybe got forgotten at the back of the freezer, you find them and like, wait a minute, these are smaller than the ice cube tray. How did they get so small? Have you ever noticed that? Or you finally clean out the ice maker and stuck up in the corner is this ugly mess of smelly ice, but the cubes there are smaller than the fresh ones that are coming out. That's because the ice is subliming in your freezer. Molecules on the surface have enough energy to escape. They escape into the atmosphere of your freezer. And then they go off and condense somewhere else, and that's part of what causes the frost buildup in your freezer. Have you ever opened an old package of tater tots or frozen French fries, and you dump it on the pan, and there's like this pile of ice crystals? Why would they put ice crystals in the bag with your tater tots? That's dumb, right? If you just bake that, it's going to form water and they're going to be soggy and nasty. They didn't do that. The water that was in the tater tots sublimed while it was being stored in the freezer. It couldn't go anywhere because it was inside the bag. It was trapped, but it moved out of the tater tots into that airspace in the bag and then recondensed and made ice crystals. And then your tater tots eventually get dry and nasty, and we call that freezer burn. So sublimation of ice in your freezer is what causes freezer burn. There's a couple of things you can do to prevent that. You can invest in a deep freeze, a freezer that keeps your food colder. The colder the temperature inside the freezer, the less sublimation that occurs. The other thing is you can wrap your food tightly or use one of those vacuum seal machines to pull all the air out of the package. If there's no air for those water molecules to escape into, they can't really go anywhere and your food will last longer. So there's kitchen tips thanks to Chem 3A. Any questions?